All right. Well, I guess can start. So we have Joanna's here as well. Welcome. Okay, I think the online audience can't see my screen yet. All right, so I'll share my screen. Share screen. So hello everybody. Okay, who do we have here online? We have I think 3 online and 3 here with me in the room. Okay, so I'll start with introduction of myself, and then maybe we can go around and just talk about ourselves. So, all right. So before I start, trying to close this. So, my name is Z. I go on the search. This is my homepage. I'm assuming online audience can see my screen sharing. Okay. Hello. Welcome. So this is me. People just call me Z. It's so the Chinese pronunciation is a bit different, but that's okay. Everybody calls me Z, so that's who I am. So in case you're wondering, why am I here talking about logic? I did my PhD at ANU, and my supervisors were two former logicians, Rajiv Gauri and Alvin Tu, and they are still at the ANU. I think Raj has retired. Alvin's still there. So I was a trained logician, and I'm really passionate about topic of logic in general and automatic reasoning and everything else relevant to this topic, especially AI. And nowadays it extends to a lot of other things. My office is at N44, it's just right down there. Yeah, so this is a reading group. So being a reading group, that means we'll be basically talking about a book. I'll be reading something. So I've got the book right here with me. So it's called Fundamentals of Logic and Computation. It's written by me. So I've got this spare copy. So if any of you guys here want to use it, you can have it. All right, so that's a little bit of introduction to myself. Well, I'm a senior lecturer now at Griffith. I usually teach in T1 and T2. So I teach courses in AI as well as cybersecurity, but this is not any of those courses. So this is just logic. Okay, so maybe you guys can have a little bit introduction of yourself.
Sure, we can do that.
Yeah, just so I know who you are.
I'm Tessa. So I'm committee member of the Griffith Technology Association. I'm currently a PhD candidate. My special interest is interaction design. But yeah, keen to hear a bit more about what this is about. So that'd be pretty cool.
I'm Phaedra Stevens. My background is neuroscience. I decided to be about thinking things. So
Neuroscience. Nice.
I'm James. I'm a mechanical engineer.
Okay, mechanical engineering. So we have people from all of different backgrounds. And
I'm Lachlan. My background is data science and applied mathematics, but it was finance.
okay, data science, finance. Very nice. Okay, so how about our online audiences? Did you guys want to take turn and talk a little bit about yourself? Maybe just one sentence. Tell us who you are.
Is my mic working?
yes, it is.
Yeah, yeah.
Yeah, cool.
mic is on.
Thank you. My name's Brock. I'm at the Gold Coast campus. I'm currently in psychological science, but I would like to transfer to computer science this year.
Okay, welcome. How about Ariana?
She just responded that studying science, work in IT is interested in the topic.
Nice. Okay, science. Okay, beautiful. Who else? Joanna? Okay. Tushar? That's all right. I'm in chat.
China, and I'm studying comp sci, majoring in data science at another institution. Grateful to be.
Okay. All right, so we actually have people from different uni as well. Perfect. Okay. So let me go back to my homepage. And the book we'll be reading is actually right here. So it's I've got a link in my authored books, Fundamentals of Logic and Computation. So in this reading group, we'll basically, I think, mainly read the first part of the book, which is about logic and automated reasoning. Second half of that book is about the theory of computing. And we actually have a course at Griffith teaching that. So we won't be going into too much details there. So there's a link on Springer. So Springer is one of the major publishers of academic books and publications. And you see, so the book is 60 euros, but when I connect to this website, where Griffith Wi-Fi, I can actually download this for free. So I think everybody here can download that for free. I'm not sure if people from other institutes. It depends on in your institute's agreement with Springer. Yeah, it depends. So this is a book. And we'll be starting from the very beginning. So the idea here is we want to provide some very fundamental introduction to the topic. And I'm not trying to lose half of my audience in the first session. So we're going to talk about logic from sometimes an informal setting. And of course, our end goal is to talk about formal logic, which will involve some mathematics, but I'll try to restrict that to a manageable scope. Okay. So the way I'm going to do it is I'm going to probably draw things. That's the way I like to do it. And I think there's a new app called Freeform. So yeah, I love it too. So I'm going to turn off my camera if I can, because I want to. I can't even turn off my camera now.
That's it.
Okay. Anyway, so we'll start the discussion of logic from the ancient history. Okay. And in the ancient history, so we're talking about thousands of years ago, when the Greek philosophers first started to reason about things using logic. When people started doing that, they first used their spoken language. So we call that formal languages. We call that natural languages. Let's write this here. So natural languages. Oh, my handwriting is really bad. If keep the iPad stand here like this. Yeah. Okay. All right, let me redo this. Yeah, but my handwriting is pretty bad in general, so. Okay, natural languages. In the old times, there was Greek, right? There was a lot of other languages: French, Spanish, English, Chinese, Japanese, a ton of those languages. So we call them natural languages. Those are the languages people speak and write and communicate. And one of the typical examples was in this kind of so-called syllogistic form. Right, so if you go to the book, you can see this. So those are the reasoning in 3 sentences. Okay, so reasoning in 3 sentences. That's called the syllogistic argument. Okay. And it typically goes like this. So we have the first sentence that says, all men are mortal. This is one of the classic examples. All men are mortal. Our second sentence is Socrates is a man. Is a man. And our third sentence goes, therefore, Socrates is mortal. Okay, so makes sense? That makes sense to you guys? So if you look at the 3 sentences, they play different roles here. Okay, they play different roles. So the first 2 sentences are sort of the premises. Okay, and the third one is a conclusion. So what's happening there is you assume that the first sentence is true. You also assume that the second sentence is true. And then you can conclude the third one. Okay, so from premises, we derive conclusions. So this is a typical form of inference. Okay, typical form of inference. And so this kind of reasoning kept going for thousands of years until one point, mathematicians thought that maybe we can formalize this a little bit. Okay, so we'll talk about the word formal a lot in here. The word formal, in the broad sense, it just means expressing the ideas in mathematics. Okay, so if something's formal, then it's formulated in mathematics. And the idea is when we talk about things in natural languages, in English right now, it can be ambiguous. So if I say something, you may understand it in different ways, right? Especially I'm not even a native speaker. And what our goal in mathematics is we want to express things in a unique way so that everybody would understand it in the exact same way. So there's no ambiguity. Everything is set and everybody understands it in the exact same way. So back in about 1600, so there were mathematicians, Leibniz. See, have you guys heard of this name, Leibniz? So he was one of the pioneers in a lot of domains in mathematics, especially in calculus. So yeah, the other day when I had a little discussion, talk with Tessa, so we talked about Leibniz and Newton. So these 2 guys were roughly in the same era, and they didn't get along well. So they were sort of competitors. Differential equations, yeah, exactly. Yeah, so there were arguments like that, and rumors said they had a lot of arguments. Newton even hired somebody to basically humiliate Leibniz, near his apartment, and things went really ugly. So, bad things happened. So see, this is really good. thing on. So when I talk about things, if you have any ideas or you've got anything to say, feel free to interrupt me. This is not lecture, right? So this is basically a discussion group. And if you see anybody saying something in the chat, feel free to let me know. Yeah.
That's wild, but like they're drama in the math world. They're like having a go at each other in a math.
Yeah. There was a really good mathematician and computer scientist here at Griffith. His name is Rodney, I think, and he's retired now, so he's no longer working. But I had a lunch with him a while ago, and just discovered it's a really small world. So see, my PhD supervisor was Rajiv Gauri at ANU, and Raj did his master's degree at the University of Melbourne, and his master's degree supervisor was Rodney. So see, everybody's linked together. So Rodney was like, it's like my grandpa from the academic point of view. So he's retired now, and yeah, the other day when we were having lunch together, he told me. So somebody asked a question. Are you still active in writing, research papers and doing, academic research? And he said, not really, since he's retired. He said he's lost something, right? And the specific thing he said he was lost was just a little bit of arrogance. So he said that to be a researcher, not a top researcher, just an average researcher, or even the PhD student, I guess especially PhD students, because PhD students are usually first authors when writing papers these days. You need to have a little bit of arrogance. You need to believe that what you're doing is the best in the world.
Yeah.
Right? You need to, otherwise you can't really publish. So there was that, and he said, he nowadays he's just being nice about everybody else's work. And
So he's not one of those ones doing like the really nasty reviews when you try to submit something.
yeah, no. So yeah, but back then, I think Newton, especially if you think about people like Newton, he was the best in what he was doing. Right? He was best in the world, top in the world. And so it's okay for him to have some arrogance. Yeah, so I think you all know his quote about standing on the shoulders of giants.
That was good. There you go.
And he wasn't being modest. Right? So if you think he was being modest, he was not. I think the context was, again, somebody was evaluating one of the contributions Newton did, and the other guy said, look, this is just incremental. Somebody's done this, the idea was similar. Of course, you did it slightly better, you put things together, you improved it a little bit, but the idea was there. And then Newton was mad, right? So Newton was angry, and he had some argument with the other guy. And in the argument, he basically just said, yeah, right, I was standing on the shoulders of giants. So that was the context. Anyway, yeah, so we were talking about Leibniz, digress, but this is a reading group, all right? So we're going to, digress a lot whenever we talk about things, we think of something else.
I wonder what Leibniz would think of us talking about Newton when we're trying to talk about Leibniz. I feel like he'd give him a
Yeah. So Leibniz thought about this idea to express the logical reasoning and inferences using symbols. So the key word is using symbols. Okay, and being a mathematician, you know what they like, right? They don't just like English alphabets; they like Greek alphabets. It's got to be alpha, beta, gamma, delta, whatever, right? And all those other symbols you use to connect things together. So he thought maybe we can formalize things so that we no longer use natural language to, express our ideas. We can do everything using symbols. And then in about 1900, there was another mathematician called Hilbert. And Hilbert promoted a program, right? So like a project, like a big project those days. And that project was about, well, it had a lot of subtasks. One of them was to formalize all of mathematics in one theory. So all of mathematics in one theory, and then having some sort of mechanical way so that you can reason about things in that theory. So what he meant was like this. So I think it's best if I draw that in some sort of Venn diagram, because people like Venn diagram. So what he meant was we first need a very small set of usually it's called axioms, right? So we need a very small set of axioms. And axioms are statements that you assume to be true, right? So those are the minimal things you need to bootstrap everything else. Right? So you can think of axioms as the minimal things that bootstraps everything else. So you've got a very small set of things, axioms, and then you need some inference, some mechanical ways of inferencing using axioms. So basically you assume that axioms are true, and then from there you deduce something else. All right. So it's like the three sentences we had just now. So the 1 and 2 are assumptions, and from there you can deduce a third sentence. Okay. You can deduce something else. So there's a separate thing that talks about how to do inferences. Okay. How to infer. So there's a box, and this is a method that tells you how to infer things from what you already know. And once you've got these two, you can take some axiom, and then you can infer something else. And that something else, if it's not an axiom, then we call it a theorem. Okay, so a theorem is something that is valid. It's something that you deduce from axioms or from other theorems. Okay, so from there you can build up your knowledge. All right, so it's also possible you assume that two of those axioms are true, you deduce something else. You get a new axiom, you get a new theorem. Right? And it's also possible that, from an axiom and a theorem you have already proven, you can deduce another new theorem. Okay, so you build up your knowledge base little by little. Okay, and then in the end, you end up having a very large set of theorems. Okay, very large set of theorems. And Hilbert's program was about determining this set of very minimal set of axioms and making sure that your set of theorems, so the set of things you can deduce, includes everything we want to talk about in mathematics. Right? So he wants to have a minimal set of axioms from which you can deduce everything in mathematics, and he wants to extend that to include everything that you can deduce in physics, chemistry, and whatever science. So that was his idea. That was his idea. And obviously, the set of axioms needs to be small, right? Otherwise, your knowledge base is too big, and you can't memorize so many things. So it's best if your axioms are a small set of as possible, right? And of course, you want it to be a finite, at least you want it to be a finite set of things. Right? It cannot be an infinite set. Okay, whereas the set of, so this is finite. Set of axioms, it's a finite typically a small set. Right? And then you have your theorems. So this big set of theorems, it can be an infinite set of things. So this can be an infinite set of things that are valid. Okay. Hmm? What's that? What's the question? Yeah. So how to infer? It's a separate thing. So those are a set of rules, right? So that's disjoint from the axioms, but those are the rules you use to infer other things, and we'll see a lot of examples. Okay, we'll see a lot of examples probably in future sessions. I'm not sure how much we can cover in today's session, but those are the things we'll certainly see a lot. Okay, so set of axioms, and how do we infer this box? Is a set of rules, set of inference rules. Okay, now I can replace this how to infer as I'll make it a bit more concrete. It's a set of inference rules. Inference rules. Okay. And then and that's a separate concept than the axioms. Okay. Two different things. So you use the rules and you use axioms and you derive new things, and new things are the theorems. So that's the idea. Okay, so that was Hubert's program, and it turned out to be way too ambitious. So spoilers alert, it's not possible. Too bad, it is not possible. So I think in the 1930s, Gödel, the first mathematician that showed it wasn't possible, and actually he showed something that is a lot worse. And basically, it was like an earthquake to the mathematical world. So he showed something that basically broke people's mind about how mathematics worked. And I think in some future sessions, we'll talk about it. Not today. Yeah, he probably broke his own mind as well. And Turing was also so that was I think what you said was it. So that was if you know that was so Gödel proved some completeness theorems, and he also proved some so-called incompleteness theorems. So the incompleteness theorems give you the sort of negative results. It says it is not possible for this very big set of theorems to be complete in the sense that it covers everything we need in mathematics and physics and everything else. It is not possible. Especially, assuming that you want to start with a finite set of axioms, then it's certainly not possible. It could be possible if you have an infinite number of axioms, but we can't really manage an infinite knowledge base, right? Because none of things we deal with are infinite. We've got computers these days, but that's not infinite, right? The hard drive is finite. It's big, it's huge, but it's finite. Nothing we deal with is really infinite. So we can't really assume an infinite set of axioms, unfortunately. So, and Turing, I haven't talked about Turing yet, but I'm assuming everybody here probably knows Turing, Alan Turing. There was a movie about him, I think starring Benedict Cumberbatch.
That's probably about the extent of what I know about Turing.
So
accounting, first computer stuff.
I think if you enroll in the course Theory of Computing at Griffith, the course should talk about him. See, he was fundamental in theory of computing. I think Turing's work is mainly in, he did a lot of work in cryptography, the breaking code. And obviously, it helped the British Army a lot during the World War II. Somebody even estimated that, so he built this machine called Enigma, and somebody estimated that it basically ended World War II 2 years earlier than it's supposed to be. It's very impressive. So by the end of that war, British Army and of course extend to USA Army, they already knew what Germans were talking about, and Germans didn't know. So British people, British Army, especially the high-level decision makers, they had to pretend that they didn't know, and sometimes they had to send people to the wrong place where they knew they were ambushed to keep it secret. But it did save a lot of people's lives. So that was Alan Turing, and one of his fundamental work in this area is it's called Turing machine. So it's a kind of abstract machine, state machine that has a tape storage. I think I'm not even sure you guys know what a tape is, because when I was a kid, I used to listen to cassette tape music players. So yes, but back in Turing's time, so I think that was again in about 1935, 1936. There were no computers, right? So computers wasn't invented at that time. So when Turing talked about computers, that English word meant something different back then. It meant people doing calculations using pen and paper, right? So from his idea, a machine that reads a tape was the natural way of how things should work. Nowadays works a bit differently, but fundamentally nothing's changed. So yeah, we were talking about the idea, the idea of formalizing things in symbols. And that's fundamental. That's fundamental in nowadays development of logic and automated reasoning. Because what we want to do in the end is not just to do things on pen and paper, right? So that's too much for us. So we want to let computers do things for us. We want to tell computers, this is a set of rules. These are the set of axioms, infer theorems for us. Tell us what is right and what is wrong. So that's what we want computers to do, right? And that is automated reasoning. And if you think about what computers are good at, I think fundamentally they are good at repetitive manipulations of symbols. So of course, nowadays computers are pretty good at analyzing and processing natural languages. So you've seen ChatGPT, it's very good at analyzing natural languages. But at the fundamental level, what your computer is doing is it's doing basic binary operations of zeros and ones. Right? So from that, you can build up very complicated applications. You can build ChatGPT on top of that, but fundamentally it's doing logical gates on binary numbers. And of course, since we talked about ChatGPT, so I had this example. So it's pretty good at processing natural languages, and you'd be asking how good is it at doing logical reasoning. And we had this example I talked with Tessa before, and it's not really that good at logical reasoning. Right. So maybe we do some experiment right now. So last time I checked, it failed. Maybe we can check it live and see if it succeeds. In that example, I need to get that example from somewhere. Okay. I actually got that example originally from Facebook. Also, I was following a computer scientist called Moshe Vadi. So Moshe Vadi is a logician. He said Rice University in the USA. And I think he either got the Turing Award or he was very close. He was one of the top computer scientists. Because for computer scientists, the top award you can get is Turing Award. Right? It's not Nobel Prize because it's no Nobel Prize for computer scientists. Right, so this is the question. It says if A implies B and not C implies not B, and A is true. So the question is C true? All right, so let's think about it. So for the online audiences, also think about it. Let me copy this and see if I can copy this. So think about this, all right? And in the meantime, let's fire up ChatGPT. I think I've got another account. I probably need to log in. My Microsoft account. Yeah. Yeah. All right.
I think the bathroom when I'm wearing a mask and wearing glasses.
Moment of truth. So maybe ChatGPT is improved over time. I mean, they usually update their model once in a while. It hasn't even updated their model about this particular question yet. Very interesting.
Obviously, I'm gaslight ChatGPT thinking that 2 plus 2 equals 5. There's a lot of messages are 2 gaslight ChatGPT is my favorite thing. I can't gaslight it. This is why you in ethical classes.
Yeah, you need to do it ethical.
Otherwise, it would implement in the
There we go. See what's funny about ChatGPT is even if it's wrong, it's trying to make it really convincing.
Yeah.
Right?
Doing BS in a very convincing way.
Yeah. So I guess if you ask another student who's outside here to read the response, it actually makes a lot of sense.
Domain knowledge is very convincing. I asked a medical question to consider a pop. It's like use like good terminology structured it well. But I feel like a medical practitioner just say makes no sense.
Yeah.
It's like am I using the right word or like completely different context?
So, but what do you guys think of this this question though? What would your answer be?
Symmetry. So like with B, can't just say B inside C, is that right?
I think you're probably overthinking it. Okay, so the issue with our current session of reading group is that I haven't introduced those logical operators yet. Okay, so it talks about implies, but the question is what is implication? What does it really mean? So I haven't talked about that yet. So there may be some barrier right now, but let's hope we clarify this by the end of today's session. No.
An idea online.
Okay, let's have a look.
And it was during the pandemic. So
I'd like to do it again, please.
that's very cool.
Okay, so Okay, not yet. That's all right. That's okay. All right.
Sorry. I was-
That's all good. So I think we can finally, well, one last thing before we finally get started with the actual content of the book. There was this idea of the basic elements of a logic. Okay, the basic elements of a logic. So there are three basic elements of a logic. So there's the syntax. We call it syntax. And what syntax tells you is in the context of logic. Right? So in logic, we formulate everything in, we call it logical formula, singular, formulae or formulas, plural. So a syntax tells you how to write a legit formula. Okay. If you want to be a bit more formal, how to write a correct formula. Well,
It's fine.
okay. So there is a there actually is a formal term for this. It's called well-formed. Okay, it's called well-formed.
Okay.
It means it's syntactically a formula. Okay. Second concept is called the semantics. Okay, so in general, if you think about any language, not formal language, not logical language, say any language, semantics tells you what does a sentence mean, right? The meanings of sentences. If you apply that in the context of logic, means the meaning of logical formulae. And by meaning, because we're talking about most of the, well, especially the logics we talk about in this reading group will be it's called two-valued logics. So everything's either true or false. It's nothing in between. Everything's either true or false. So in that context, the semantics tells you, given the formula, is the formula true or false?
The meaning.
It is basically the meaning, right? Given the formula, is it true or false? So that's the semantics. Okay, and there's a third concept called a proof theory. And the proof theory is essentially a set of inference rules that tells you how to infer true formulae or valid formulae. Okay.
Hear me twice. Twice.
We'll try that. There we go.
A set of inference rules for deriving valid formulae. Okay. And of course, there are other concepts in this domain as well, but we'll start from these three. So, given a logic, if you know its syntax and semantics, you basically know everything about this logic, right? Because you know which formulae are correct formulae or well-formed formulae or not well-formed formulae, and you know if they are true or false. That's basically all you need to know about the logic. And alternatively, you can focus on the syntax and proof theory. All right, so well, syntax is necessary. You need to know which formula is a correct formula in this logic. But proof theory helps you to derive valid formulae. So it's a way of deriving valid formulae. If you know that, then you know, given any formula, you know if it's true or false. Okay, so those are the three basic elements in the logic. All right, and we're going to start with our first logic in this reading group. And it's called propositional logic. It's called propositional logic. Propositional logic. Okay, so this is our first logic. And we'll have other logics. There are actually a ton of different logics. So propositional logic, the concept is actually quite simple. And I think most of you have dealt with it in your daily life. And there's a closely related concept called Boolean algebra, which is actually one of the most basic, logical algebraic systems. You probably have learned about Boolean algebra in your high school. I think typically that's high school material.
Yeah, I remember a little bit. Oh, the one with the diagrams.
The diagrams?
Like circles.
I know what you're talking about here. I know what you're talking about. We can draw those diagrams in a second. And by matrix, I think Tessa was talking about truth tables.
Maybe. Oh, the truth table.
So we can have a review. We can have a review of those concepts. But before that, we need to understand the syntax first. We need to understand the syntax. So with propositional logic, what are the key elements in the syntax? Well, there are two logical constants. Okay, logical constants, and those are called true and false, respectively. That's simple, right? So true. Oops, what am I writing? That's not true. True and false. True and false. And if you are a computer science student, you can understand it from a programming language point of view. I think if you write a programming language, anything, most of the programming languages, you'll have true and false as the constants of Boolean expressions. Okay, true and false. So I reckon if it's in a program, then it wouldn't be capital T and capital F. It's usually lowercase t and f. Same thing, right? So true is true, false is false. Not much to talk about. Except when we write logical formulae, we may use slightly different symbols. So we use a T, it's true, and the upside down T as false. Okay. So this T is also called top, and the upside down T is called bottom. Okay, true and false, but they just mean true and false, so nothing special about them. And there are a few ways you can compose formulae or Boolean expressions if you think of a programming language. So this not, okay, so not, I'll write that not. If you're writing an expression, Boolean expression in a programming language, you will usually write an exclamation mark. That's usually an exclamation mark. All right, I think it's an exclamation mark in C, C++, Java, Python, probably in 99% of the programming languages. And again, when we talk about logical formulae, we'll use a slightly different symbol. We'll write this. Okay, so the symbol is called not. And sometimes some people would use a tilde. That's also not. So this is just different ways of writing the same thing. Okay. What else? What other Boolean operators do you use in your programming languages? And or, all right? So those, I think those are the fundamental ones. So we have and. How do we write it in programming languages? It's usually 2 ampersand signs. Yeah, looks like this.
I'm thinking of SQL, where you literally write and.
Yeah, you can write the English word as well, but I think in most of the programming languages it's 2 ampersand signs. And again, in logic, we use a different symbol that looks like this. Okay, and or. So how do we write it in programming languages? How do we write or in programming languages? The vertical bar. You usually have 2 vertical bars. That's or. Right? 2 vertical bars. That's or. And in logic, again, we'll use a different symbol. So we'll use upside down symbol of and. So that's or. Okay, so those are the basic symbols. We're talking about symbolic logic. Those are the symbols. Okay. And then there's the semantics. The semantics of those things actually not too difficult. I think most of them are quite intuitive, I'd say. You probably don't need me to explain what is not. It's just the opposite of whatever else you're trying to say. Right? And it's also quite straightforward. If you've got A and you got B, A and B is true when both parts are true. Right? So the or, I think or is the only thing that's a bit tricky. Or is the only thing that sometimes is understood differently in English. To English, when you say or, come on in.
Oh, hi.
Hi.
Oh, sure.
Yeah.
Yeah, come in. So, hello. So in English, when you say or, you often mean exclusive or. It's a bit different.
This or that.
You can have this or that, but usually you imply that you can't have both. Yeah. So there was this joke from the TV series. It's called IT Crowd. You watched IT Crowd?
I watched all of the IT crowd.
I think in one of those early episodes, somebody asked Moss about the name of a girl. The question goes, is it Julie or Judy?
Julie, okay.
And Moss goes, yes.
Ah.
See, that's a typical
Anytime.
that's a typical understanding from a programming language or from a logician's point of view.
Yeah.
All right, so the answer to that question is yes, because it's true.
Yeah.
Think it is in English?
Yeah. So in English, you usually think of it as in exclusive or, but in logic and in your programming languages, it's the inclusive or. All right. So the truth value of A or B, well, of course, depends on the truth value of A, truth value of B. But A or B is true if one of them is true.
Yeah.
And you don't care about the other one.
Yeah.
As long as one of them is true. So that's the I think that's the semantics of the basic operators in logic.
So it's the same as like if you're
I mean, I think it seems like the main place where I've used it is probably in SQL.
Mhm.
It's all the same.
It's all the same. It's all the same. In SQL, in your databases, in your programming languages, they are understood the same way. So maybe I should write inclusive OR. So this is an inclusive OR. If any of those things are true, then the OR is true.
Even if it's both of them are true.
Yeah.
If both of them are true, then it's also true. If one of them is true, the OR is also true.
When we're just saying it's like to have one of them not true. The other one is
Yeah. So that's
Yeah.
exclusive OR.
both.
So if you want to draw some Venn diagram, okay, this is your formula A. What is not A? Not A is basically everything else,
Yeah, memories from school.
right? That is not A. Not A is everything else. You got A and B. This is A, this is B. A and B is their intersection, right? A and B is true. When A is true, and B is true. And we talk about A or B, then it's the whole thing. You call it the uni, right? So A and B corresponds to intersection. So now that you're talking about intersection and union, so that is how you write intersection in mathematics. That is how you write union in mathematics. You see, it's intersection is the opposite down of union, so the opposite of union, and this opposite of OR. You see, there's a lot of symmetry in logic. There's a lot of symmetry in logic. And not is set minus the subtraction of on the set. Okay.
That's all totally.
So those are the basic elements, but we haven't talked about an important thing called implication. What is implication? I think this is going to be the last thing we talked about in today's session. Implies. Okay, and you don't usually have a symbol for this in programming languages, but it's very common in logic. Okay, so in logic, we write an arrow. Okay, we write an arrow. We write an arrow. So what does imply mean? If we say A implies B, what does it mean? Okay. Or we may also write A arrow B. It means you assume that A is true, and then you can derive that B is true. So it means, in English, it means if A is true, then B is true. If A is true, then B is true. That's what implication means. Okay. But the tricky case is, what if A is not true?
Does that mean that B would also be true? Would also be not true? Or not necessarily.
Not really. So the value of A implies B is true. So think of A implies B as one thing. This thing is true whenever A is true, B is true. Okay. But if A is not true, then that means your assumption is wrong. And when your assumption is wrong, it doesn't really matter what you conclude. It doesn't really matter what you derive. Okay. So if A is not true, it doesn't matter if B is true or not. This implication, it's called vacuously true. Okay, it's trivially the implication is trivially true if your assumption is wrong. So it sounds a bit weird.
Feel like we'll get there.
Okay, it sounds a bit weird, so I'll give you some time to process that because this is the end of the session. Yeah, so let's take one example. Because if today's raining, then everybody here is a billionaire. Okay, if today's raining, it's not raining.
It's not
right?
raining.
Today's not raining.
So that-
You know that today's not raining. So this indicates, so the statement that I just said, if today's raining, then everybody here is a billionaire. This statement is true. Okay, it's trivially true because today is not raining.
And no one has a billionaire.
So it doesn't matter if everybody's billionaire or not.
Oh, okay.
Okay, so the logical concept is if you assume something wrong, then it doesn't matter what you argue. Right, so that's the idea, you know, don't argue with somebody who assumes something wrong because you can't really win the argument.
Is it because like a true can only be like a finite kind of thing, whereas a not true can be like,
Oh, that's a very interesting idea. That's very deep. I think sometime in the future session we'll get there. Sometime in the future session
look that one way back.
we will get there. But I guess for today's session, all you need to know is A implies B actually is equivalent to there we go, not A or B. Okay, it's equivalent to not A or B. So this is again, you probably need some time to process this, and we'll continue from the next session. What does not A or B mean? It means if today is not raining, then you know that the left part of or is true. Then the implication is true, so you don't care about the rest.
Oh, okay. Still boils down to being an or statement, and as long as one
So-
thing or the other is true, it's true.
So implication in the end is an or. That's why we didn't count it as one of the basic elements up here. So in your programming language, any programming language, you can still write implications. You just don't use a single operator to write it. You will use not A or B. All right, so you can still express implications in your daily programming language. You just don't use a single element. You just don't use a single operator to write. But the concept is there. All right, it's a composition of not and or. So I think we'll end today's session. To come next week, we'll continue with implication. We'll probably finish this example of ChatGPT and analyze why it's wrong. So I'll take a screenshot. Okay, so I'll take a screenshot. So next week we will continue from here. All right. So let's end today's session. Thanks, everybody.
Blowing my mind. I feel like I've been more on the
Okay. All right. See you.